So now we do one thickness, but multiple spans. Okay, same sort of input at the beginning. And now this time, we have a range of spans, and we put it in as a one-dimensional matrix, so an array. So length is equal from 2.5 meters up to 7.5 meters. And from that, we can get our load span table for this particular panel. So it's a 100mm thick panel, and all we're doing there is taking the bending moment equation and turning it on its head to give you the loading that would cause the panel to fail in bending. And the loading in the fixings based on that is simply given by this equation that we've seen before. Take half the load and the spacing and multiply by the length. So we're looking at the spans here, and we come out with the fixing loads here. Spacing required to keep the fixing loads below the fixing capacity. Given that you've got a fixing capacity in each fixing of 1 kilonewtons, then it varies from the 198 millimeters up to 594 millimeters. Checking on shear, we're looking at the shear equation again turned on its head. From that, we get what load will cause the panel to fail in shear, and that's where we have an array. Now we need to transform our section again, which is what we've done before. We calculate the elastic moment capacity. In this case, it's 3.11. And then we look at bending failure for that. So what we saw before with plastic bending failure, now we're looking at the elastic bending failure. So this is likely to be the limitation for an aluminium section. Then we look at mid-span deflection limitations. So we're going to limit our deflections under serviceability limit state to span over 150. So again, you'll recognize that equation as the flexural bending for a simply supported beam. And then we add on to that the shear deflection because of the PIR. And then we put it on its head and say, well, that's our limit, LP over 150. And then we vectorize it, and out pops a load span table going from 3.3 kPa all the way to 0.36 kPa, depending on your span. So that's for serviceability, but we want to turn those into ultimate limit state loads. So we use a USR, that's an ultimate to service ratio. In this case, it's the square of the wind speeds, because remember, wind pressure is proportional to the square of the wind speed, and it pops out as 1.479. This, of course, will vary depending on what region you've got. And now the new wind code has made it a little bit more complicated by having different ratios in different wind zones. For the purpose of this exercise, we'll just happily use the 1.479. So we pop out with a ultimate deflection limit at 4.87. So this is the load which will cause a 2.5 meter span panel to fail in deflection. So we can summarize spans by using the transpose sections. And the reason we are transposing them is so we can draw graphs from them. So for some reason, Mathcad only likes to draw proper plots and proper charts using vertical matrices. So we use the matrix function transpose, which you can find under the matrix table under T, and it turns your horizontal matrix into a vertical matrix. Simple. From that, we can produce our plots. So you've seen above, we've turned span into the transposition of LP, bending into the transposition of W under 100, and then again shear for WV 100. We then pop in a plot, and the plots are found on the plots menu, insert plot, and we put our traces in. So we've got 3 traces on the y-axis, bending, shear and deflection against the span. And in this case, we've chosen different colors for each. And oddly enough, deflection is now governing those loadings. So that was one thickness with many spans. So now